Hello, everyone, and welcome to this month's Space Telescope public lecture series. Today, we have a really great talk about the interstellar medium, where gas, dust, and stars meet. So I have a joke that I am obligated to tell about the interstellar medium. If an astronomer received a signal from a long-dead civilization, does that make them an interstellar medium? Okay, bad joke. Anyways, my name is Dr. Kelly Lipo. I am, in fact, not Dr. Frank Summers, who normally hosts these lectures, but I'm here today because he is on a well-deserved vacation. And I'm also joined tonight with my tech team, Thomas Marufu and Grant Justice. Grant will be monitoring the YouTube chat. So if you have any questions for our speaker or you want to discuss things among yourself, please put all of your questions in the chat. So a little bit of housekeeping before we get started with tonight's talk. On October 3rd, 2023, we have a talk from Nimishi Karamari, oh my gosh, sorry, I butchered that name. Nimisha Kumari, there we go, from the Space Telescope Science Institute, who's going to tell us about web science. Sorry about that, oh my gosh. On November 7th, 2023, we have a talk from Tim Rue and Margaret Carruthers from the Space Telescope Science Institute, also about making astronomy outreach accessible to different types of audiences, including blind and visually impaired people. And then in December of 2023, we have the infamous TBA, where Frank will find another speaker and let you all know about it shortly. So on the topic of knowing about upcoming events, if you would like to get notifications about upcoming events or see any of our past live streams, you can do that on our website at stsci.edu/public-lectures. And there are links for webcasts, recordings of past lectures, and also email sign up box, put your email in there and get notifications about upcoming events. So how do you get in contact with us? As I said, you want to sign up for emails. I think they send like 2 emails a month. You can sign up at the website, stsci.edu/public-lectures. You can subscribe to this here YouTube channel. That's youtube.com/Hubble Space Telescope. And there you'll get notices and reminders about live events just like this one. And also, if you have comments, you can email publiclecture@stsci.edu. You can complain about how I just messed up those speakers' names. I feel so bad about that. You can tell Frank that you miss him and you wish that you were back, or you can say, you know what we need? We need more of Kelly on this YouTube channel, so let them know. Follow us on social media. So we have lots of different social media accounts, whatever flavor that you're interested in. And so these are in order of the Hubble account, the web account, and the STSCI account. On Facebook, it's Hubble Telescope and Web Telescope and STSCI. On Twitter, it's @Hubble Telescope, @NASA Web, and @Space Telescope. On YouTube, it's Hubble Space Telescope and NASA Web Telescope. And on Instagram, it is space_telescopes and NASA Web. And if you are looking for someone else to follow, I am primarily on Mastodon, which is sort of like Twitter or X, but more chill and just a wee bit more nerdy. You can follow me @KellyLipo @astrodon.social. And Frank also told me that I can do a news from the universe segment, and you should all be very proud of me that I am not doing just a weird star news segment. I will actually tell you about some really interesting stories that have come up over the past month or so. So our first story tonight is about a new view of the Whirlpool Galaxy. So this is a very old view of the Whirlpool Galaxy. This is an image from the Atlas of Peculiar Galaxies compiled by Hulton Arp in 1966. This is a photographic plate taken with one of the big telescopes in California, maybe the Palomar Observatory. I don't know exactly which one, but this was the state of the art in 1966. Let's see what the state of the art was in 2005. Here we have the Whirlpool Galaxy as seen by Hubble. And here we actually see two pairs of galaxies which are interacting with each other. We have the Whirlpool Galaxy, which is this beautiful grand design spiral in the center. And we also have a companion galaxy off to the side right at the end of one of its spiral arms. It's a lenticular galaxy. And these two galaxies are actually in the process of merging with one another. And that's probably why the Whirlpool has such beautiful, very clear spiral arms. Okay, so that's what it looks like with visible light with Hubble. Let's see what it looks like with Webb's infrared eyes. Ooh, look at that. So Webb just imaged this strip in the middle of the Whirlpool Galaxy, and we can zoom into this a little bit. It looks like that. So here we have the dark red features which trace the filamentary warm dust, and the colors of red and orange and yellow show gas in the galaxy that was recently ionized by clusters of blue stars, which are those blue dots in the image. If we, though, move on to the mid-infrared view, we get the really wild image from Webb here. So this in mid-infrared light, what Webb is primarily seeing are filaments of dust and molecular hydrogen and other molecules in the galaxy. So what do I mean by dust? And I think Alex might get into this a little bit. By dust, I mean teeny tiny particles of sand and things that kind of resemble soot. And so we are seeing here these cold, dusty clouds inside of the whirlpool. And we also see these filaments, which are these areas carved out by clusters of newly forming stars. I think someone on social media said that this looked like a biblically accurate angel, and I, think that maybe they're onto something. It's both creepy and beautiful at the same time. Okay, moving on to our second story of the evening, cosmic question mark. So here's where I get to talk about weird star news, at least in the beginning. So here is a 2013 image from the New Technology Telescope from ESO's La Silla Observatory in Chile. This is a ground-based optical telescope image of this cold, dark, dusty cloud. And inside of this cloud, we have a pair of newly born stars which are orbiting each other. You can't see them in this image, but what you can see is this jet that they're blowing out. And they're actually blowing out a jet above and below their disk, but we're only seeing one of the jets in this image because the other jet is actually embedded inside of this dark, dusty cloud. Okay, let's switch over to Webb's infrared eyes. And here we are seeing through this nebula, and we are seeing the full jet made by this pair of baby stars. And we can see the cavities that are being carved out inside of the jet. The walls of these cavities are glowing. The stars themselves are that bright red thing in the center. You can see the bright red diffraction spikes coming off of these stars. But wait, there's more. Some eagle-eyed Redditors spotted something while they were staring at this image. So, computer, enhance. We are going to zoom into this image. There we go. Okay, and let's try that again. What is that? So the internet has dubbed this the cosmic question mark. And going back to our first story of the evening, we don't quite know what this is, but we're pretty sure it is a pair, or maybe even three, galaxies, which are about to merge together. And as galaxies merge together, they tug on each other with gravity, and they can make some pretty interesting arc-like shapes. And so that's what we think the cosmic question mark probably is. If we could see it in a little more detail, it might look like this. And so this is a Hubble visible and near infrared light image of another pair of merging galaxies. And you can see this kind of question mark-like shape. Okay, that's enough from me for tonight. I am not who you came to see. Instead, we are going to hear from Dr. Aleksandra Hamanowicz. Dr. Aleksandra Hamanowicz is a postdoctoral researcher at the Space Telescope Science Institute, where she studies gas in and around galaxies using the Hubble Space Telescope. She is originally from Poland, where she finished her undergraduate studies at the University of Warsaw. Afterwards, she continued her astronomical journey as a graduate student at the European Southern Observatory in Germany. Aleksandra, privately an avid choral singer, lives in Washington, D.C. with her husband and her rescue lab, Gidget. And we were in a call right before this, and we said, we can't tell everyone about your rescue dog, Gidget, without showing a photo. So here it is. Here's Gidget. Everyone say aw. Okay, and without any further ado, I am going to hand things over to Alex. Take it away.
Thank you so much. Just making sure everything is fine. Hello, everybody. Great. Thank you so much, Kelly. Hello, everyone, and thank you for joining me for this journey through the galaxy, where we're going to learn a little bit more about the area of the galaxy where gas, dust, and stars meet. I had a wonderful introduction with some of the aspects I'm going to talk a little bit about. So you saw beautiful filaments of dust in other galaxies. We saw all of these wonders what James Webb are showing, and I will hope that I can give you a little bit of the insight about what we are actually seeing and how astronomers are studying this elusive interstellar medium. If you were lucky to view the night sky somewhere very, very dark, where you actually, apart from the thousands of stars, could also see the trail of the Milky Way, you would immediately see the difference between the strain of the Milky Way and all of the rest of the night sky, as it shows us this cloudy, very extended structure on the sky. And even more than with our naked eyes, when we look at the longer exposure photographs or videos like this one, we can definitely see some sort of a structure, another cloudy-like structure and some darker areas. And what we are actually seeing is we are looking throughout the disk of our galaxy all the way to its center, and we are looking through the interstellar medium. Because when we will be thinking about galaxies and about stars, we could think that this is this gigantic space filled with nothing and those singular stars so far away from each other. We just often hear that travel between the stars will take so many, many years and even generations. And so that makes you think that there is nothing in between there in this vast empty space. But that's not entirely true, as this whole of the space is filled with gas and dust. But let's not be confused with how it appears on this image, like the cirrus-like clouds. In fact, this is still very high vacuum, and even this gas and dust in the interstellar medium, it's not as dense as air or clouds as we experience them every day. It's much, much less amount of particles. So even though on the pictures it shows up as something looking like a cloud, in the end, it's not as dense as that we would imagine. So continuing this view of rather elusive, very diffuse medium in our Milky Way, let's take a look at our whole sky as if we could see on the north and in the south, if we will be able to do that. And that's what one of the satellites from the European Space Agency, Gaia, did. It scanned the sky to create the map of our whole Milky Way, of everything we can see from Earth. And this is what it looks like in in the visual light, so in the visible light, so the same one as we are looking at every day with our own eyes. And majority what we are seeing is starlight. Now, stars are all over the place, everywhere on the sky, and they are especially congregated along the disk of the Milky Way. This is not the only thing which we are seeing here. We also see those dark patches of clouds, which we call dust lanes, which are exactly where the manifestation of the interstellar medium through those dark dusty patches. But that's just mostly stars again. If we were looked at the same image, so again on the all sky view of our Milky Way, but trace particularly the emission coming from the gas, and we can do that in the radio and microwave, also from the sky, from the space. Sorry, when we can use, for example, in fact, in this view from the Planck satellite, what you will see that this all of the space is filled with hydrogen, is filled with this cold gas, which forms filaments and clouds, and just filling the whole of that space. And that's exactly what interstellar medium is. And basically, it's also in its name. It's everything, all of the gas, which sits in the space in between the stars in the galaxy. And it's not only our own Milky Way, but also all of the other galaxies, just as we saw on the picture from Webb, which Kelly was showing earlier in a whirlpool. But also, interstellar medium does not have a very strong cutoff, so that we get to some certain number of light years from the disk and then suddenly it ends. No, there is no strong barrier. All of that gas is disappearing gradually. However, if we look at the sky in the X-rays and look at the very, very hot gas, it shows what we astronomers call the circumgalactic medium. Now, that gas is more of the gas which was expelled from the galaxy through the eruptions of supernovae, through strong winds coming from stars, or even from some activity in the center of our galaxy millions of billions years ago. So this interstellar medium transitions into the circumgalactic medium, which in turn transitions into intergalactic medium. Gas is everywhere. Hydrogen is everywhere, even in between stars and in between galaxies. Again, it's not very dense, and we cannot see it very easily, but it's there. So let's go back inside our own Milky Way and use it as a model for how a typical galaxy looks like and how a typical interstellar medium looks like, and what's happening in there. Why is it important? Why are we talking about it today, and how we can study it? And I think the most important aspect of the gas in between the stars is the fact that stars themselves are being born in those dense gas clouds. So you need to have this material in order for new stars being formed. And for the galaxy to keep evolving and to keep living, it has to keep forming new stars. And that's basically how the cycle of life in a galaxy goes. We need the gas, and we need the gas for the new stars to be born, for the galaxy to be kept alive. And while the material is being used by the stars when they're being formed, after they live a very long life, they produce a lot of material in their interiors, the new elements. In the end of their life, they expel all of that material back into the interstellar medium in some sort of a cosmic recycling or baryon cycle, how we call it. But this is not exactly the same material, because some of it was used by those stars in the process of nucleosynthesis to form new elements. Therefore, each of the dying star is in fact enriching the interstellar medium with more and more heavy elements. Now let's talk a little bit about this interstellar matter in a bit more detail. What exactly it is, what kinds of matters we are there, what actually is being built of, and where we can find it when we are looking at the, let's say, images from Hubble Space Telescope. In general, as I started at the beginning, even though this gas is everywhere in the galaxy and the galaxy is vast, the total mass of this gas is really, really tiny. If we take all of the stars in the galaxy and put them all together, we have what we call the galaxy stellar mass. And if we take all of the gas and dust, it would be maybe 5 to 10% of this summed mass of all of the stars. Of course, if we add even dark matter to that, we are talking about really small percentages. But even in comparison to stars themselves, the amount of that gas and dust is really small. Majority of this gas is in the form of hydrogen and helium. And for those of you who already are following this kind of talks, you probably realize that hydrogen and helium are astronomers' favorite things, and also universe favorite things. They are everywhere. Everything is made out of hydrogen. Every galaxy, every star, everything is made out of hydrogen. It's because hydrogen and helium were the first things to form after the universe began in a Big Bang, and form in such vast quantities that up to this day, even though the stars are burning the hydrogen in their cores, still hydrogen is the dominant element in the universe. So it's no surprise that it's also dominant in the gas in between stars within the galaxy. But as I said, there is a small percentage of what astronomers call metals. And again, it's a running joke that astronomers and chemists can never agree on to what a metal is. We astronomers like to call everything heavier than helium a metal, which every chemist is going to take their hands and up to the air, because how can you call an oxygen or sulfur the metal? But it's just to look at it very simple. Hydrogen and helium formed very long time ago with the creation of the universe, while the rest of the metals are being formed in the nucleosynthesis inside in the cores of the stars. And that's how we are distinguishing those two kinds of elements. And it's nothing to do with the chemical properties, really. So excuse me for using the metals later to name all of the elements which maybe in the chemistry we would not call it this way. So the one thing about this percentage of metals in the gas is also varies depending on what galaxy we're looking at. This 2% is more or less for Milky Way. But if we will be looking back in time into those very distant galaxies which Webb is currently discovering, we could see that the percentage of metals in them is rather smaller. And it's because the stars didn't have enough time to form all of the metals in their cores. While in those billions of years later, we are here in the Milky Way in current time, it was enough time to build up this still small, but a significant percentage of metals. That's a very important fact, which we astronomers, when we study the evolution of galaxies or the environment of different galaxies, have to remember that the gas we are looking at in those very, very far away objects might differ from the ones which we know from Milky Way. Some of the small galaxies like Magellanic Clouds or other dwarf galaxies in our local neighborhood also will have a smaller percentage of those metals because they form less stars as they are less massive, and therefore in that way, even though they had enough time, they didn't have enough stars to build up the metal percent. So those metals also, each of them have a different abundance in the interstellar medium. For example, carbon, nitrogen, or oxygen are the very most popular after the hydrogen and helium, mostly because it's the very first thing which forms in the stars. The next ones and the heavier elements require more and more extreme temperatures, pressures, and extreme situations for them to be formed. And from all of those different elements in the interstellar medium, the ones which we find the most, apart from carbon, nitrogen, or oxygen, is also magnesium, silicon, or iron. Those last three are especially found often in the dust grains. Here on the right, I'm showing you the picture of a cosmic dust particle brought to Earth by emission stardust. And it was the mission which was trying to gather any of those particles in our solar system and bring it back to Earth so we could actually, under the microscope, take a look at the stardust. And this is how it looks, and you can already see by the scale that it's a teeny tiny thing. This is nothing like a dust which we are used to every day in our homes or a grain or any grains on the ground which we can find. This is very tiny. In fact, the dust grains can be smaller than bacteria. So that already shows you the trick, how tricky it is for astronomers to study. We are very used to something which is gigantic, like galaxies, while now we have to study something teeny tiny, which is more for the domain for the biologist. What is also interesting about the dust is that apart from those elements by themselves, it allows for creation of the molecules. So, for example, those cosmic dust particles often have molecules of water or carbon monoxide, or even some more complex organic molecules forming on their surfaces. So they are kind of a first surface for those more complex chemistry to be formed, which in turn becomes very important in the formation of the planetary systems. All right, so we now know a little bit of what this interstellar medium consists of. So let's see where in the galaxy we actually can find some interesting regions in this whole gaseous medium, which fills a void in between the stars. So I'm going to tell you about 3 areas of this interstellar medium, which is very important in astrophysics, not only because what they are themselves, but also how we can use them to study distant galaxies. And I will start from this beautiful example of a diffusion nebula, or the emission nebula, which we astronomers also call H2 region. This is usually a nebula of hot gas surrounding young stars, and the Orion Nebula is one of the examples, which means that the recently formed young, very bright stars are sitting behind that, or within this gaseous nebula, and lighting it up and hitting it with a lot of this radiation. What gas does, or especially the atoms, what they do when they are hit with the radiation, is that they get excited. And quantum mechanics tells us that each different element will react to the light in a different way, in a way that it's going to absorb this energy and then shine in a very specific, very narrow chunk of light, which we call the emission line spectrum. And here on the right, you can see the examples of those atomic fingerprints of the different elements. So each of those elements will have a very specific and one and only set of the small chunks of lights, the spectrum. Thanks to that, we can, in a very big distance, just by looking at the light of a region like this, tell what it consists of, how much of different elements actually there is in this gas, which is being lit up by the stars. And actually, we are using this technique not only to understand the nebula in our Milky Way, but even very, very distant galaxies. So with all of those galaxies very far away, which James Webb is finding all the time, to study it, we do not see anything. It's just a blob, right? We do not see stars. We do not see gas or dust lanes. This is just a round red blob. But by looking at the spectrum, we can notice the emission lines, which correspond to those chunk of light which we expect for the element to emit if it's being lit up by young stars. And thanks to that, we can say what kind of elements there are in this very, very, very distant galaxy. Plus, by a little bit of a deduction, we can also say, okay, we know that for this kind of light to form, we need to have a young stars shining at the gas. So maybe we can deduce somehow how many of those young stars there are in a galaxy, and then in turn say how many stars in this galaxy on average is forming every year. That's called star formation rate, and this is what we also can deduce by measurements like that. So even if for the galaxy is very, very far away, we can say a lot just by looking at their light. So that's about those beautiful nebulae or H2 regions, which show a lot of this emission line spectrum. Let's look at the more dense and more colder clouds, called molecular clouds, like this example of the Horsehead Nebula here. These are slightly different regions. This is where the gas is actually getting very dense and very cold. And this is the ideal environment for dust. Dust is very, very delicate, and it's very, very difficult to have dust particles in the regions around young stars. It's too hot, and the dust evaporates. The water, the particles, everything is going to be destroyed. So the dust is only found in the regions which are very dense and very cold, so that the cocoons of gas can actually shield the dust from the radiation of those stars. And usually, because of this whole shielding and this density, those nebulae appear dark, because no light can penetrate and can go through. So in that way, we know that inside the dust is comfortably sitting and can get forming bigger and bigger things. In fact, those very dense gaseous nebula are cosmic nurseries, because the denser the material gets, and these very cold molecular clouds, at some point due to gravitational collapse, it can start forming a protostar. And that's what one of this Carina Nebula is one of those places. So even though we see a lot of young formed stars, I can guarantee you that in those very, very dense, very dark clumps of gas, which we are seeing here, some new stars are being formed. It is very interesting when we are thinking about that, because those molecular clouds are often, especially in the visual light, found as the places where there is no light and there are no stars. And for example, as we can see on those images, when you can see them against the very dense and stellar background, they just look like the holes in the sky. But in fact, they are so dense molecular clouds that any light of the star can penetrate them, and that's why inside there's a very good place for stars to form in peace. So if you look even deeper, and these are the images from Hubble Space Telescope of the nebula in Orion inside of the very dense clouds of it, you can see a very, very small globally, even smaller and dense in pockets of gas where the actual stars are being formed. Each of those images shows a small pocket of gas in which the star with its unique planetary system is being formed. Because before the star lights up its internal engine and starts pumping radiation at crazy rates, it's still rather small and rather cool, and still gets the material to form and get more massive from the surrounding cloud. And that's also an excellent moment for the planets to start forming. And here comes the dust again. Because while we were talking that the interstellar medium is full of hydrogen and helium, the dust is mostly of all of those small metals. And on Earth is not built from hydrogen. Earth is built from all of those other elements or heavier elements. So planets really need dust particles to start up this collection of material, which in the end can form the solid surfaces of them. So therefore, it shows that even though it's very tiny, the dust plays a very important role in the formation of the planetary system. So there is also the last aspect of kind of nebulae or kind of areas in the interstellar medium, which I would like to touch. And this is about the stars which are dying. So after millions of years of creating the elements and heavier elements in their cores, eventually they run out of hydrogen to fuel the reaction, and stars pass away or fade away. And that's where they return the material which they were formed from, plus these new elements which they formed, they return into interstellar medium. It's a baryon cycle of the interstellar medium. Smaller stars, and by that we call the ones which are of a mass less than 8 solar masses, so our sun is included in this group. When they reach this moment in their lives, in the center, they start to form the white dwarf, and all of the rest of the star starts to lose connection to this very teeny tiny core, which is now so small that it just does not connect anymore with all of the rest. The star starts to pulsate. It sends out the pulses of gas, and the outermost layers usually got dispersed into the space. This is one of the images from James Webb telescopes showing exactly that process. You can see a nebula with those very distinct circles of waves, which was each pulsation, the star was losing another of its outer layers. So those stellar pulsations help to remove the layers of the gas from the star. And in the end, what was being formed is what we are showing here, which is the planetary nebula. So all of the material which star was made of is now dispersing into the interstellar medium. Plus, of course, the metals which were formed in the center. However, because of this process can be a little lengthy, like you can see the pulsations it's taken still millions of years, it becomes a very good environment for the dust to form. Again, dust needs to be in a cold, dark place, and though those waves of gas being expelled from the star actually are a very good place for it to start forming. So those kind of stars not only create metals, but also create the actual dust particles. If we look at the larger stars, so the stars which are more than 8 solar masses, we have slightly different situation because those guys are going out with a boom. Definitely, when they reach the creation of iron in their cores, there's no way for them more to go, and they expel the outer layers in a very quick and catastrophic ejection of material with a very high velocity. What remains are those nebulae, which we know as supernova remains, and the principle is kind of similar to what we saw before. However, there is an additional formation of even heavier elements during the explosion. Thanks to this extra energy, we can push more neutrons into the cores of atoms to create even heavier elements. So in the supernova explosion, not only we do exactly all of the stuff with the smaller stars with the returning all of the material enriched, we also create even more elements. And that's as the cycle of life in the interstellar medium. We start from the dense gas clouds, in which they're getting denser, and eventually through the gravitational collapse in those very dense molecular clouds, we can form protostars with their protoplanetary systems in the dense cocoons of gas surrounding them. But then, when the star starts to radiate in the full energy after starting the nuclear synthesis in their center, it can take millions of billions of years for it to keep creating those new materials. And then, at the end, it returns all of that material with a little extra for the new generations of stars and planets to being formed. Nothing's going to waste in the interstellar medium, and we are all set in this circle of life. So I hope I showed you that even though the interstellar medium, or the gas in the interstellar medium, as well as dust, even though that they are only a small percentage of a general mass of the galaxy and maybe require a little bit of a hassle to actually see on the images or through telescopes, it actually does not mean that they are irrelevant, because stars and planets form from exactly this material. And dust play an extremely important role in the formation of especially planetary systems, and also in the creation of this advanced chemistry of this proto-organic molecules and organic molecules. We still do not understand how we go from a very basic organic chemistry into life on planets, but that connection has something to do with the interstellar dust for sure. And now I would like to switch gears a little bit, and now that we understand the importance of the interstellar medium and all of that material, how we astronomers actually study it. I already hinted that it's a rather elusive and diffuse medium and might not be that easy to detect or understand. And one of my last points on this slide is that the dust contributes significantly to the galaxy radiation. So that's one of the other aspects of how dust is important in our understanding of galaxies. So how do we actually study the interstellar medium? Well, I'm gonna tell you a little bit about physics of what happens when there is a stellar light hitting the interstellar cloud of gas and dust. And there are several things which can happen, and each of them tells us something different about the nature of the gas, which is in between us and the star. So one thing which can happen, and it mostly happens to the blue light, is reflection. Light can be scattered or reflected off to the dust grains, and it's the part of the light which feels it the most is the blue light. So those form the kind of a reflection nebulae, which you, for example, could see around the Pleiades, as I showed, or this is another example of a very bluish looking nebula. What we can say from this reflection is mostly where the dust is located, and also a little bit about how big the grains are, about the size and where they are, and how many of them they are, because that will on that will depend how much the reflected light will there be. I also highlighted the excitation, which I already mentioned earlier, that in the some of the nebulae, the reflection is not enough. The light is strong enough to excite the elements on the atoms in the nebula, and they start to shine with their very characteristic set of emission lines, and that helps us understand the star formation also in distant galaxies. But let's move to the other aspect of the dust, which is thermal emission. So one of the things which can happen is that when instead of exciting the elements like the atoms, when we have dust particles, it's not just getting excited, it's getting warmed up. And anything which has a temperature higher than 0 Kelvin, so anything which has higher temperature than -460 Fahrenheit, actually emits infrared radiation. So we can here see a picture of a dog, just a dog. But if we point an infrared camera on it, what we will see is a slightly different image. We immediately see that there are bright spots where the dog is very warm. We know that the dogs use their mouths and their tongues to cool themselves down, and that's where they are very warm. Also, their eyes are very warm. But their nose, and if anybody who has a dog can say that, is rather cold. And this, what you can see with pointing the infrared camera at the dog, is going to be the different parts of the dog, depending on how warm they are, will be brighter or darker with infrared radiation. Infrared can also help us see invisible things. So on the picture on the top, you can see a picture taken in the zoo at night. And again, with our just in a visual light, we're gonna see nothing. But if we point infrared camera, we can see a bird. So you can see that even though for our own eyes, we actually do not see anything, the infrared can already tell us something about the object being there. It's enough for the object to have a temperature to actually radiate and to radiate in the infrared. And dust is exactly the same. The interstellar dust has the same principle. So we can tell about the temperature of the medium, and we can also look at study the actual properties of the dust by looking at its radiation in the infrared. And James Webb Telescope actually helps us immensely with this task. On the very left of this picture, you can see what I call warm part of the pillars of creation seen by Hubble in the visible light. So more of our own usual human eyes kind of looking. But if we go into more and more infrared, we are going to look into more colder and colder things. So first, what we're going to see is that we are going to look through this nebula, which is on the background on the picture on Hubble. Suddenly, there's plenty of stars. They were hidden behind that light. But with infrared, we can look through and we can see how many stars are being actually formed in pillars. But if we go even colder, the image starts to blur up again. But now this is not the gas emitting, this is dust. So all of the glow, all we can see on the mid-infrared is actually it's a radiation of the dust itself. And with that, we can actually study the properties of the dust. We can link the amount of radiation we see with amount of dust, with its temperature, and also with its structure. What kind of elements are there? How is it built? All of those answers we can now get thanks to the James Webb Telescope as well. There's one other very interesting aspect of what happens when the light hits the cloud of the interstellar gas, and it's called extinction. Extinction is when not all of the light is going, so some of the light which was not absorbed and then re-emitted, some of the light which was not reflected, some goes through, but it goes through red and dim. So what we can do is we can look at the stars in our Milky Way, and say, I can expect how this particular star should be. But what I'm seeing is that it's redder and it's dimmer than what I expected. And based on that, I can deduce how much dust is there in between me and the star to cause this effect. It sounds a little elusive, but the extinction we could see very well during the Canadian forest fires, when the cloud of fire smoke came and colored our skies. And like on this picture from the New York, we can see this orangey sky. The same happened with the wildfires in California, and this orangey dim light. But probably even if you live on the East Coast, you could notice that something was not right with the air on those days. And this is exactly what extinction is doing. The light from the sun didn't change. What changed is that the air became polluted with all of those particles of smoke. And what ended up that not only the light was orange, so it got more red, changed the color, but also it was much dimmer. And that's exactly what extinction does. So in theory, we could take the pictures from the days of Canadian wildfires and make a map of the dust or the smoke in the sky. And that's exactly what we are doing when we are studying stars and their light in the Milky Way. So here is actually, this is not the picture, this is the map of the dust distribution based on the measurement of extinction. So using all of the stars, which are laying all over the sky, we compare them to what we expect them to look like, and then we create this map of dust. So this is exactly what we astronomers have to do every day to understand what actually is sitting there in this diffuse interstellar medium. And for the very last bit, I would like to say about an absorption. And this is something which is the closest to me because this is how I study the interstellar medium. So what is absorption? Well, it's something a little opposite to when we were talking about exciting atoms and emitting the particular chunks of light. Atoms not only excite, but they can also absorb. That means that when you have a star behind the interstellar cloud, the same chunks which would be emitted by the nebula of light can be absorbed, so can be eaten away from the light of the star. And when we look at the star and then we can see in its spectrum those eating away bits, we can do exactly the same what we did with the bits which we are emitted. We can say, aha, there is a fingerprint of a particular element right there. And each element has a very specific set of lines, which makes it very distinguishable. So that's what I do. I look at the stars and Milky Way and in other galaxies, and I look at the spectrum of them and try to identify the elements. And from that, I can also deduce how much of different elements are actually in the dust form and how much are in the gas in those interstellar clouds. So I hope that I showed you all of the different ways that we astronomers have to come up with to understand the interstellar medium. It's still elusive, it's very diffuse, and it's not right there to the picking. We have to sometimes come and think of many weird and clever ways how to measure something, and then from that measurement deduce something which we actually are interested in. And those measurements can be very tricky, and we are using everything which we can, from ground-based to space telescopes, to try to understand the nature of this very elusive, but that very important interstellar medium. And with that, I'm very happy to take your questions. Thank you so much for listening.
Great. Thank you so much, Aleksandra. That was a really great talk. And I can say, as an astronomer, so I think there are two types of astronomers. One type of astronomer who gets really excited about dust, and one type of astronomer that gets annoyed that dust is in their way. And I was always the second type. I had to correct for the dust when doing my observations. So I think as the host, I get the prerogative to ask the first question. So I guess I'll start with something you mentioned at the very end. So for your research, what you're doing is you are looking at spectra, and you're trying to figure out what sort of elements are in the interstellar medium. So what elements are you looking for?
So mostly I am looking for iron, magnesium, and other and sulfur. Let's say these are the easiest ones to detect, and also especially magnesium, iron, or silicon are the ones which are the main components of dust. So we are mostly looking at those, and would like to know how many of the total amount of those elements in the particular gas cloud actually is in gas, and how much it sits and forms the dust. So those are my favorites. Let's say iron, it's definitely my favorite.
Oh, awesome. I'm glad you have a favorite element. Okay, and another question for you. So you're talking about using the Milky Way as sort of a model to understand other galaxies. So how different is the interstellar medium between different galaxies? How does the Milky Way compare to other galaxies, maybe like the ones we're seeing with Webb?
Oh, definitely. If we compare the Milky Way to some spiral galaxies in our neighborhood, that's basically looking at very similar, especially in terms of interstellar medium. If you're looking at the galaxies which Webb sees in those deep fields, which are those very, very old objects, then we are talking about a completely different environment where stars haven't formed as many metals yet. And actually, we don't exactly know how this interstellar medium looks and that far away, and don't know how similar or different it is to Milky Way. On the other hand, when we have those small dwarf galaxies like Magellanic Clouds, those also will be slightly different. They often they do not have the structure of the spirals and a nice disk. They often are so more puffy, or they have gigantic star formation regions like Tarantula Nebula. So they have those very, very different dynamics within them. And then also we have those which some could call dead galaxies, where there's no dust, no gas, no stars are being formed, and their interstellar medium is some remnants which are not enough to form new stars. So there's quite a diversity there.
Cool, great. So Grant, are there any questions from the chat?
Hello. Yes, absolutely. We've had a very active chat today. It's been great.
Awesome.
So I'm going to get started with this one with the caveat that this may be more of an engineering question, but you deal with the data enough. Do you know what the range is that can be measured? So what you generally look for when you're looking for dust, gas, whatever it is that you're doing, what is the general range in the spectrum that you're searching?
Oh, I see. Well, that's really depends what you would like to look at, because as I mentioned, let's say if we would like to see the signature of those different elements, depending on the element, they will come at different regions of the spectrum. So, for example, I am studying only nearby objects, where the light is coming into ultraviolet. That's why I'm studying it with the Hubble Space Telescope. That's the only telescope who can actually reach that. So we are looking at the ultraviolet, and that's where all of those metals sit. When we are looking at, let's say, emission lines from those emission nebula, which I was saying, and then we are looking for those elements to say, oh, where is the hydrogen, where is nitrogen, etc. Then we are looking into, nominally, we are looking into the visual band, so that's more familiar to us, unless we are going very, very far in time, when the redshifting of the light comes into play, and everything which is nominally in this visual band goes far into the infrared, and then we have to use Webb. So, in truth, to have a whole view of the interstellar medium across different times and across different distances, we have to go basically from ultraviolet to the far infrared, and some of the hydrogen shines very strongly in radio. So to be honest, you can go in any aspect and you will find some emission or some signature of the interstellar medium.
Awesome. Thank you. Which kind of leads us into the next question, which is, I know that we have multiple observatories and multiple stations that we use, but how many light years away would you say you can measure within your error margins?
Okay, so what I am doing right now, let's say, So using this absorption line method, it's very nearby. We are going into maybe up to Andromeda galaxy, let's say that. And I have to say, as an astronomer, I do not have idea how many light years it is from us. I don't know if you, for the other in the other talks, it was definitely everything we operate in parsecs and megaparsecs, which is very weird unit, which I don't never like to explain. But let's say Andromeda galaxy absorption lines. With the emission, because those lines are so strong, we can go very far away. And Webb showed that we can go 13 billion years, billion light years, right? So it's far away. So that all depends on the kind of the measurements we are doing. With radio, we also can only go not that far, let's say, to the Whirlpool galaxy, right? So it really depends which wavelength, which light we are observing, and which characteristic you're looking for.
Yeah, so I just looked it up just to help you out.
Thank you.
The Andromeda galaxy is 2.5 million light years away. So in astronomy, that is very close by.
That is pretty close by, yes. And I feel very bad now, not knowing how many light years that is.
Okay, I had to Google it. It's fine.
You're fine. Trust me, if there's one thing that the audience is good at, it's asking the questions that you didn't think you needed to know for the talk.
As I said, we operate on parsecs and megaparsecs, and I really hate introducing that to the general public because it's such a weird unit that even I don't really remember the full definition.
It's all good. All right, so how significant is dust in the extragalactic medium, and how does it impact on our images or our science looking at very distant objects? How often is it an obstruction?
$1 million question. Actually, I would say that there are two camps in the astrophysics right now. One saying that there's hardly any dust out there, and one's just saying there's plenty of it. And up to today, we really do not know. The problem is that what I was trying to say during my talk is that dust is a very delicate creature. It really needs specific environment to thrive. And the moment it's accelerated too much or it's warmed up too much, it's being destroyed. So in the way we're thinking that for the gas to, for the dust has to be first formed somewhere and then shoot away from the galaxy. That's why we think that it's actually not that much of it in the intergalactic medium. Unless, for some reason, there are clouds of very dense clouds of material in which this dust could be formed. But this is rather, we haven't found anything like that. So this is still a very open question, how much of the dust there is. But in terms of abstraction, the main source of abstraction for our observation from the dust is from our own Milky Way. Because as I showed you those pictures, there's all of the interstellar medium is all over the sky we can reach from the Earth. And then our own Milky Way, which is full of dust and full of gas, can actually cause us extinction and all of the other effects, which actually affect our observations, and we have to account for them. And that's why scientists like me have to study this dust so that all the other scientists can know how much they have to correct their own measurements, which actually is more of a problem that I think we fought before Webb.
So that leads lovely into the next question, which is, what is the most significant way that JWST has impacted your work?
So for definitely there are aspects of the parameters of the properties of the dust which were very, very difficult to understand from Earth without space infrared telescope. For example, studies of the organic molecules. So I was mentioning that dust is a great place for those very complex chemistry to start forming. And there is a particular kind of those particles, which are called PHs, polycyclic aromatic hydrocarbons, if I'm correct. They are very complex sheets of actually carbon, which we do not know much about, but we kind of see them out there in their signatures, in their light signatures, and Webb can perfectly study them and tell us how many of they are, where they are, and maybe how they connect to more complex organic chemistry, which we see on Earth, or hopefully on some other planets in the future. But that's the James Webb definitely comes in here. And MIRI, so the mid-infrared, is especially wonderful. This is probably one of the first times we have such a wonderful mid-infrared instrument, because it shows you exactly where the dust shines. So you can point it anywhere and then just lights up the whole dust, which in other ways is very hard to trace.
Okay, Grant, I think we are running short on time, so maybe one or two last questions.
All right, deal. I'll end on this one then. What is the most unexpected discovery you have made while studying the galactic medium?
This is a wonderful question. So one of the unexpected things which I found is actually very, very recent, and hopefully is going to be published soon. Which astronomers love this.
We get the pre-published tea. I feel honored.
I was very interested, especially in studying the formation of dust in low metallicity environments. So in those dwarf galaxies I mention all the time, in which they didn't have enough stars to form enough metals in their interstellar medium. So what we see when we study their stars is like, oh, it looks like they have only like 5% of the metals that Milky Way has. And we were thinking, how does dust form in such environment when there's so little metals? And we thought, oh, probably there's hardly any dust. No, actually, it seems like there is nothing stopping. I mean, apart from the fact that there's less of the dust because there's less of the material, but there's no some dramatic change. Suddenly, dust is not forming in dwarf galaxies. It's still there. And I think this is my most unexpected thing. I thought it's going at some point we're just going to be like, there's no more dust. We are reaching the critical amount. But it seems like even in 5% solar, we are still forming dust.
That's really cool. Yeah.
Okay, folks, I think we are going to have to end it here for today. Thank you again, Aleksandra, for that lovely talk and telling us all about the gas and dust between stars and how that interacts with the life cycle of stars. Thank you to everyone in the chat for the lovely questions. And I won't be here, but Frank will see you all next month for another talk in our public lecture series. Okay, thank you, everyone.